72 inches, 6 feet of snow. That is the number that the National Weather Service office in Buffalo, New York, recorded across a single 7-day window in November 2022. A lake effect event so catastrophic, so historically anomalous, that meteorologists who had spent entire careers studying Great Lakes snowfall sat in front of their models and read the output twice before they believed it. 47 people dead, thousands of vehicles stranded on highways that became open-air freezers. A Buffalo Bills NFL game relocated to Detroit because the stadium was physically unreachable. That event, the November 2022 lake effect siege, was supposed to be the kind of thing that happens once in a generation. The kind of snowfall sequence that gets its own Wikipedia page, its own chapter in the regional memory, its own permanent place in the conversation about what winter in the Great Lakes corridor is capable of producing at its absolute extreme. It was supposed to be a ceiling, a benchmark, the reference point against which future events would be measured and found lesser. What is developing right now is not lesser. And the reason that statement deserves your full attention is not simply because another significant snowfall is on the way. It is because what is currently assembling itself across the northern tier of the United States is not a single storm. It is a sequence, a rare, structured, atmospherically coherent sequence of back-to-back snowfall events arriving on the same geographic footprint with a timing and a stacking architecture that snow scientists and climatologists have a specific term for. They call it a snow siege, and the one building right now is carrying credentials that the historical record has almost never seen in this configuration. Here is what most people do not understand about record-breaking snowfall, and it is the single most important concept for understanding why what is developing now is different from a bad storm. Records do not fall because one storm is exceptionally large. They fall because a sequence of storms arrives in a pattern that prevents recovery between events. The greatest snowfall totals in recorded meteorological history, the 95 inches at Tamarack, California in a single month in 1911, the 140 inches at Mount Baker, Washington across a single season in 1998 to 1999, the 104 inches in 24 hours at Silver Lake, Colorado in 1921, were not produced by a single enormous storm dropping an impossible amount of snow in one pass. They were produced by atmospheric setups that kept delivering, kept reloading, kept sending organized precipitation into the same drainage basin, the same mountain range, the same lakeshore corridor, again and again before the previous events, snowpack had time to compact, settle, and be managed. The ground never recovered, the snowpack never stabilized, the infrastructure never caught up, and the totals that resulted were not the sum of individual storms. They were the product of compounding, of each successive inch of snow falling on a surface that was already at or beyond its capacity to absorb what came before. That compounding dynamic is precisely what is now in motion across a corridor stretching from the eastern Great Lakes into the interior Northeast and the upper Ohio Valley. And the atmospheric architecture supporting it is not a 3-day event. It is a multi-week pattern lock that the models have been showing with increasing, uncomfortable consistency. To understand the sequence, you have to start with the pattern driver, the large-scale atmospheric configuration that is not just producing individual storms, but is manufacturing the conditions under which storms keep forming, keep tracking through the same corridor, and keep depositing snowfall on the same geography. The feature responsible is a persistent, anomalously strong ridge of high pressure parked over the Gulf of Alaska. A ridge that has been sitting in approximately the same position for the past 3 weeks, and that the medium-range models show no sign of dismantling for at least another 2. Atmospheric blocking of this kind, a ridge that resists the normal west-to-east progression of the jet stream and forces it to route around a fixed obstacle, has a downstream signature that is as predictable as it is consequential. When a strong ridge blocks over the Gulf of Alaska, the jet stream is forced to dive sharply southward over western North America before climbing back northward over the central and eastern portions of the continent. The result is a persistent deep trough over the central United States, a trough that acts as a storm, track highway, funneling organized low-pressure systems from the plains into the Great Lakes and Northeast in a procession that, under the right moisture and thermal conditions, deposits historic snowfall totals one event at a time, each one landing before the last has finished being measured. The snowfall totals that have already accumulated across parts of the eastern Great Lakes corridor since the beginning of this blocking pattern are not modest. Across the traditional snowbelt counties of western and central New York, Erie, Chautauqua, Cattaraugus, Wyoming, Genesee, and the southern and eastern suburbs of Buffalo, snowpack depths have been running at 150 to 230% of the seasonal average for this point in the calendar. In isolated terrain-enhanced locations in the Tug Hill Plateau of northern New York, a geographic formation that functions as a natural snow amplifier for lake effect systems coming off Lake Ontario, seasonal snowfall totals are already approaching the upper range of what the historical record shows for entire seasons, not mid-season benchmarks. The Tug Hill, which holds the distinction of being the snowiest location east of the Rocky Mountains, has recorded individual seasons exceeding 400 inches of snowfall. Several monitoring locations within the plateau are currently tracking at a pace that, if the blocking pattern persists on the timeline the models are indicating, would challenge seasonal records that have stood for decades. This is not a projection built on worst-case model scenarios. This is an extrapolation from observed snowpack data already on the ground, combined with a pattern forecast that has been showing multi-week persistence with high model confidence for the past 10 days. Let's be specific about the sequence itself, the individual events that have already occurred and the ones that are now in the pipeline, because the specificity of the timeline is what transforms this from a general winter concern into a documented, measurable, record-threatening sequence. Event 1 landed 3 weeks ago. A classic Alberta clipper reinforced by a strong upper trough deposited 18 to 26 inches across the traditional Buffalo snowbelt in a 36-hour window. Before that event's snow had been fully cleared from secondary roads, Event 2 arrived 6 days later, a deeper, slower-moving coastal low that drew Gulf moisture northward and produced a heavy, wet snowfall accumulation of 14 to 22 inches across the southern tier of New York and northern Pennsylvania. The kind of dense, high water content snow that snaps tree limbs, collapses poorly maintained roof structures, and adds weight to snowpack at a rate that fundamentally changes what the next event's additional accumulation means for structural loading. 3 days after Event 2 concluded, Event 3 developed a Great Lakes lake effect machine triggered by a sharp Arctic air mass crossing Lakes Erie and Ontario with water temperatures still running several degrees. Above the seasonal average, deposited an additional 2 to 4 feet across the primary lake effect snow corridors in a 72-hour period. 3 events, 11 days. And the atmospheric pattern that produced all 3 of them is not only still intact, it is, by every metric the models are tracking, strengthening. The lake effect component of this sequence deserves special treatment because it is the mechanism that distinguishes what is happening in the Great Lakes corridor from a typical multi-storm winter and elevates it into the territory of genuine historical rarity. Lake effect snow is produced when cold Arctic air masses cross the relatively warm open water of the Great Lakes, picking up heat and moisture from the lake surface, destabilizing dramatically as they do, and depositing that moisture as intense, highly localized snowfall on the downwind shorelines. The intensity of lake effect snow is directly proportional to the temperature differential between the air mass crossing the lake and the lake surface temperature. The greater the differential, the more explosive the convection, the heavier the snowfall rates. Lake surface temperatures across Lakes Erie and Ontario are currently running 4 to 7 degrees Fahrenheit, above the historical average for this point in the season. This is not a minor anomaly. In lake effect meteorology, a 4 to 7 degree above average lake surface temperature is the difference between a moderate lake effect event and a historic one. It is the fuel surplus that allows each cold air mass crossing the lakes to extract dramatically more moisture than it would under normal thermal conditions. Every Arctic outbreak that crosses the Great Lakes under this pattern is essentially crossing a lake that has been preloaded with above-average thermal energy. The result is lake effect snowfall rates and totals that exceed what the air mass alone would produce under historical baseline conditions. And because lake surface temperatures cool slowly, the thermal inertia of a large body of water means it holds its above-average temperature for weeks, not days. This fuel surplus is not going away. It will be there for the next event and the one after that, and every event in the sequence for as long as the blocking pattern continues to pump cold Arctic air across those lakes. Here is a number that belongs in this conversation, and that will not appear in your local weather forecast. The current seasonal snowfall departure from normal across the primary lake effect corridor of western New York is running at a rate that, annualized across the remainder of the season, would produce a seasonal total that has been observed fewer than 4 times in the instrumental record at any monitoring location in the region. Fewer than 4 times. The instrumental record for snowfall in western New York extends back to the 1870s, 150 years of documented winters, documented storms, documented seasons. The pattern now in place is producing departure rates from that 150-year baseline that place the current sequence in rarefied territory by every statistical measure the historical data supports. This is not hyperbole, and it is not the routine overstating that attaches itself to every notable weather event in the social media era. This is the raw arithmetic of observed data compared against a century and a half of records, arriving at a conclusion that the meteorological community is discussing with the specific, careful language of genuine scientific concern. The infrastructure, consequences of a snow siege, as opposed to a single large storm, deserve the same serious accounting that compound flooding and compound tornado outbreaks receive, because the mechanisms are identical and the outcomes are analogous. A single large storm tests infrastructure. A sequence of storms destroys it. Snow removal operations across the affected corridor have been running essentially continuously for 3 weeks. Equipment that was new at the beginning of the season has accumulated the kind of operational hours that produced mechanical failures. Municipalities that budgeted snow removal costs based on historical seasonal averages have already exhausted or exceeded those budgets before the midpoint of the sequence. The specific financial figure for snow removal operations in Erie County, New York, the county that contains Buffalo and its surrounding suburbs, was reported at nearly 140% of the full seasonal budget allocation consumed as of mid-season, with the forecasted sequence of additional events still entirely ahead of them. Salt and sand stockpiles across multiple upstate New York counties are being actively monitored for depletion risk, a concern that, in a normal season, does not arise until late February at the earliest. Roof snow load inspections have been ordered for public buildings in multiple counties following structural failures at 2 commercial properties and 1 residential garage collapse attributed to cumulative snowpack weight exceeding design tolerances. These are not projections. These are documented operational realities already present in the landscape before the next wave of events in the sequence has arrived. The human dimension of a snow siege is harder to quantify than the meteorological data, but it is no less real, and it is the dimension that ultimately determines whether an extreme weather sequence becomes a crisis or remains a managed hardship. Isolation is the primary mechanism. When road access to rural and semi-rural communities is disrupted not for 48 hours, the typical recovery window after a single large storm, but for days or weeks at a stretch, as events stack on top of each other before roads can be cleared, the consequences move beyond inconvenience and into genuine danger. Medical emergencies that require ambulance access, medication resupply for elderly residents in communities where the local pharmacy has been unreachable for a week, livestock on farms where feed delivery has been interrupted by road closures that have not reopened between storms, heating fuel deliveries that cannot reach rural customers when the roads to reach them are buried under snowpack that the available equipment has not been able to clear before the next event begins. These are not edge case scenarios in the current situation. They are documented active concerns in communities across the affected corridor, being managed by emergency management systems that were designed for single event response and are being asked to sustain multi-week continuous operations with resources that were not sized for that demand. There is a climatological context to what is happening now that extends beyond the immediate sequence and into the longer-term question of whether what the Great Lakes corridor is experiencing in this season represents a departure from historical norms or a preview of what an altered atmospheric circulation delivers as its new normal. The specific combination driving the sequence, a warm lake surface providing above-average fuel for lake effect, combined with a blocking pattern delivering repeated cold air outbreaks across those warm lakes, is exactly the combination that climate researchers studying Great Lakes snowfall have flagged as a scenario that becomes more probable, not less, as the regional climate shifts. Warmer lake temperatures increase lake effect intensity for any given cold air outbreak. More frequent or persistent blocking patterns linked to Arctic amplification and the weakening of the polar vortex's containment integrity increase the frequency with which cold air outbreaks are delivered. The result is a paradox that is not actually paradoxical once you understand the mechanism. A warming regional climate producing more intense lake effect snowfall, not less, because the fuel, lake thermal energy, is increasing while the delivery mechanism, cold Arctic air outbreak frequency, remains or increases under a disrupted polar vortex regime. The 2022 to 2023 and 2023 to 2024 seasons both showed elements of this dynamic. The current season is showing it at a scale that researchers are documenting as a potential case study for exactly the kind of extreme lake effect sequence that their models had predicted would become more common, but that the observational record had not yet fully confirmed. It is being confirmed now, in real time, across a landscape that is running out of places to put the snow. The models showing the next event in the sequence, the one that is now at 5 to 7 days lead time and has been present in model output for the past 6 days with high run-to-run consistency, are describing a system with characteristics that forecasters have been noting carefully. A deepening low-pressure system tracking from the Central Plains into the Great Lakes. Deep layer moisture return from the Gulf of Mexico, feeding into the system's warm sector before cold air wraps in behind the front. Lake-enhanced totals in the traditional snowbelt corridor potentially reaching 20 to 36 inches from this single event, on top of the snowpack that is already there. And behind it, at the 8 to 10 day range, another Arctic reinforcement, another cold air mass crossing warm lakes, another round of lake effect, another deposit in a snowpack that has nowhere left to go. The sequence is not finished. By every measure the atmosphere is producing, the blocking pattern overhead, the lake surface temperatures below, the jet stream configuration in between, it has not reached its conclusion. It may be approaching its climax. It may be approaching something the historical record has no adequate precedent for. And the communities in its path are managing their fourth week of continuous winter siege operations, with equipment that is tired, budgets that are spent, crews that are exhausted, and a forecast that is not offering them the recovery window they need. The rare winter sequence developing right now is not rare because a single number will eventually break a record in a database somewhere. It is rare because of what it is doing to the land, the infrastructure, and the people underneath it, and because the atmosphere generating it is not yet done. Stay informed. Understand the sequence, not just the storm, and recognize that when forecasters use the word rare, they're not reaching for drama. They are reaching for the only word in the language that is accurate.